1.5, Transformations and Symmetry. So here's kind of a summary of the different transformations you can have. The first one, when it says f of x plus k, that just, whatever this is, it just means we're going up. And this means we're going down by whatever that number is, whatever that k is. And you've seen this before. When you add or subtract, you move it up, you move it down. When it's inside the parentheses like this, most people remember it's like opposite of what you would expect, but this one is left and this one is right by whatever that h number is. Over here, when you multiply by a number in the front, that is a vertical stretch. It gets taller. So if it's a parabola, it gets taller or it gets steeper. Inside here is a horizontal stretch, and I think this one's probably the hardest one to understand. If you were thinking about over here when it was inside, thinking about it goes the opposite, it's kind of the same thing. It almost does the opposite of what you would expect. If there was a number 2 right there, instead of stretching it by 2, it kind of does the opposite of that. All right, so we'll see an example here in a second. A negative sign in the front like this is a vertical flip. Turns a parabola upside down. A negative inside the parentheses is going to be harder to understand, but that's a horizontal flip. All right, and so a vertical flip is over the x-axis, and a horizontal flip is over the y-axis. And so that maybe seems backwards to what you would think, but if you visualize, here's the axis. If I do a vertical flip, it's gonna flip this vertically. I just flipped it over the x-axis. But if I'm going to flip it horizontally, that just flipped it over the y-axis. So it is kind of backwards from what you might expect. Number 1, I left out a piece of important information, so I want you to add this in. It says k equals 2. I want you to add in h equals 3 and a equals 4. So add in h equals 3. So perform each transformation above on the point 16.8 if k equals 2, h equals 3, and a equals 4. So I'm talking about these transformations. So basically, what I want to do is the first transformation was up. So I want to go up by k, and so that's 2. So I'm going to go up 2, and I'm going to go down 2. Because k is 2 over here. All right, up 2 and down 2. So if you look at the point 16.8, what controls going up or down is this y number. So if you just visualize where that point is, 16.8, so here's an xy point, you go over 16, you go up 8, there's some point right there, okay? If I go up 2, now those coordinates are 16, comma 10, very good. We just added 2. If I go down 2, now those coordinates are 16, comma 6. Easy enough. Now I want to go left and right. So notice that's the letter H, and so I'm going left and right by 3. So if I go left 3, if I go left 3, now we're talking about the x number. Left 3, think about 16 on a number line. If I go left 3, what number am I at now? That's going to be 13, comma, and then just leave the original number was 8. That point started at 16, comma 8. I moved it left 3, now it's at 13, comma 8. Now I'm going to go right 3. And so your 16 moves over to the right to 19. 19, comma 8. All right, fair enough. Now I think we get to the harder stuff. I think the stretching is always going to be harder. But if you look at, we're multiplying by a for the stretching here. So a was 4. I want to do a vertical stretch by what? By 4. Okay. So if you think about the math, all we're doing is multiplying by that a number. Okay. We're multiplying by the a number. And so if we multiply by the a number, the vertical stretch is going to take my point up here. If I stretch it vertically, it's just going to move the y coordinate. So really, I'm not multiplying both coordinates. I'm multiplying the y coordinate. I'm multiplying a vertical stretch. I'm changing the y coordinate. That's the vertical component. So I'm taking that 8 times 4, and I would get 16, comma 32. Every point in the function, if it's stretched vertically, is going to get multiplied by that 4. Now I want to do a horizontal stretch by 4. Okay, and this one's weird. Okay, I told you it kind of does the opposite of what you would expect. So instead of taking the x coordinate times 4, you're really taking it times 1/4. It's kind of weird. All right, you know, if it said plus, we went left. If it said minus, we went right. Well, when this says times, we're going to divide by 4 basically. And so 16 times 1/4, I want 1/4 of 16. That is 4. So 4, comma 8. That's by far the hardest one for me to understand. Maybe it will be for you too. But anyway, just think about it. It kind of does the opposite of what you would expect. I think the stretching is definitely the hardest part. Now let's look at a vertical flip. Okay, well, a vertical flip is just going to take a point and flip it over the x-axis. So really all you're doing is changing the y coordinate. So if we do a vertical flip, we change the y coordinate on that vertical flip, it becomes 16, comma -8. And if we do a horizontal flip, we're going to take this point and flip it over the y-axis. It changes the x coordinate. And so the x coordinate becomes -16, comma 8. I think that example is kind of tricky. So think it through. You're going to see one like that on your homework. So make sure you ask questions if you get stuck. Types of symmetry. For a point AB on the graph, I've got that drawn for you. Y-axis symmetry puts this point over here. If that point is symmetric with the y-axis, it puts it over there. Think about what that does to the coordinates of the point. It's no longer A, comma B. It is, what did we change? Did we change the x or the y? We changed the x coordinate to the opposite of whatever A is, comma B. And that's strange for people to think about because it looks like it says negative, and we read that as a negative number, even though it's in the positive graph space, okay? That does not say negative A, it says the opposite of whatever A is. And so it's really hard to get that through your head, but that's not a negative, that's an opposite. So y-axis symmetry takes our point and basically flips the x, okay? So it flips the x coordinate. If I have x-axis symmetry, x-axis symmetry is going to take our point down to here. Notice what changes this time is not the x coordinate, but the y coordinate. Now again, that negative sign on negative b, that does not mean negative. It really should be said as opposite b. We shouldn't say negative b, we should say opposite b. But you're taking your point and you're flipping the y this time. Symmetry about the origin does them both. And so if you can imagine flipping them both, you're going to end up over here. If I take the opposite of the A or the A number and the opposite of the B number, we're going to be there. Symmetry about the origin flips both. So it's kind of weird because for y-axis we flip x, for x-axis we flip y. Symmetry does both. How to test for symmetry. I think the graphical method is much easier. Basically, if you can just graph it or look at a graph and see what it flips over, you've got the symmetry. If it flips over the x-axis, if it flips over the y-axis, okay, you can see it most of the time when you're looking at the graph. That's easier. The algebraic method is a little bit harder, but for x-axis, you change y to negative y and see what you get. It should be the exact same equation. For y-axis, you place x with negative x. For origin, you do both. So that's exactly what we set up above. The x-axis flips y, the y-axis flips x, the origin flips both. That's what we're looking for. And then it says, note a function with any two types of symmetry also contains the third. Number 2 says show which types of symmetry are present in each equation. And so I gave you little graphs there because I think it's much easier to look at a graph. If you had Desmos out or your graphing calculator out and could graph it and could look at it, it's going to be pretty obvious which type of symmetry you see, if there is any at all. X equals absolute value of y. You should know that an absolute value is a V shape, but this one's written weird because it's X instead of Y. So this one is actually a sideways absolute value. And use Desmos for help if you need to, but that's what this looks like. It's a sideways absolute value. And to check for symmetry, all you do is look at, well, like it would fold over the x-axis. So this one has x-axis symmetry. One side of it folds over the x and completely matches the other side of it. This has x-axis symmetry. I can see that pretty much immediately when I graph this. Which types of symmetry? X-axis, not y-axis though, not y-axis. All right, now algebraically, to check this algebraically is not my favorite thing to do in the world, but if I wanted to check for x-axis symmetry, oops, hang on, try that again. If I wanted to check for x-axis symmetry, I would flip y in the equation. So look at your equation. X equals absolute value of, I'm going to flip y. And I'm just going to see what happens. Absolute value of opposite y, well, that's just going to be the same thing as absolute value of y. So really, flipping y doesn't have any effect. Flipping y, I end up with the exact same equation. So this tells me that yes, it does have x-axis symmetry. If I wanted to test y-axis symmetry, I flip x. So I'd say negative x equals absolute value of y. I flipped x in my equation, and if you notice, that's not the same equation as what we started with. You can tell that that's a different equation than what we started with, so this does not have y-axis symmetry. So that's the algebra. That's how you would do it algebraically, okay? For origin symmetry, you would flip both of them. Negative x equals absolute value of negative y. Well, absolute value of negative y is y, so absolute I'm sorry, negative x equals absolute y. That's a no. Okay. Nobody likes doing that, but graphing isn't too bad. If you look at the graph, it's not nearly that bad. So let's look at part B. Part B, that's an absolute value, so you know it's a V shape. It's shifted down 3. So there's one of our transformations, right? That's an absolute value that's shifted down 3. I like knowing the parent functions from a previous lesson. I know what that looks like. I know it's shifted down 3. So it's going to look like this. And you can tell really quickly that's got y-axis symmetry. We look at that graph, we know it has y-axis symmetry, but not the other two. Okay, not x-axis symmetry. 2x minus y equals 6. You should know that's a line, and you should be able to graph a line. Since this is in standard form, I like the intercepts method or the cover-up method. What I do is I'll plug in 0 for x, and that goes away. I have negative y equals 6. So that means the y value must be negative 6. 1, 2, 3, 4, 5, 6. That's a point down here. And then I would plug in 0 for y, and that goes away. 2x equals 6, so x must be 3. 1, 2, 3. I've got 2 points. That's going to be enough to draw a line. To check for symmetry, basically you're just trying to fold it over, all right? And if I took some point, let's say I took this point, and I folded it over the x-axis, I'm going to be down here. There's no x-axis symmetry. If I took that same point and folded over the y-axis, I'm going to be over here. There's no y-axis symmetry. I don't see any symmetry, so we would say no symmetry. You know, maybe I should have made that point before. If you take this point and fold it over the y-axis, you're at this point. That's why there's y-axis symmetry. But if you took this point and folded it over the x-axis, you don't have x-axis symmetry. So we can kind of see it on the graphs there. Part D. You may not recognize this shape, but it's a, anybody know? That's a circle. Okay, that's a circle. Specifically, that's a circle of radius 5. So how I would graph a circle is I would go over 5, up 5, over 5, down 5. I've got a circle of radius 5. That is a circle of radius 5. So you can look at this and you can say, okay, this point, if I reflect that over the x-axis, I'm down here. That's got x-axis symmetry. Okay, that's got x-axis symmetry. If I take this same point and flip it over the y-axis, I'm good with y-axis symmetry as well. Okay, origin symmetry says take this point and flip it over both. Right here, it's got all 3. But remember, that note said if it's got 2 of them, it's got 3 of them. Okay, so this has all 3. It has x-axis, y-axis, and origin symmetry. The next one is the disco function, and I don't expect you to know how to graph all of these without a graphing calculator, but I'm kind of trying to do it fast, because if you don't graph it, then you have to do it algebraically. And it's not like you can't do that. So let's do this one algebraically. All right, if I tested for x-axis symmetry, I'd flip y. So negative y equals negative 2x cubed. And yeah, I said negative. I should have said opposite. The y's would cancel out. I mean, the negatives would cancel out. That's not the same thing as what I started with, so it does not have x-axis symmetry. I can tell without graphing that it does not have x-axis symmetry. So if I do y-axis symmetry, let's check for y-axis symmetry. I flip the x, so y equals opposite 2 times opposite x cubed. Okay. You've got a negative cubed. Basically, what you've got is 1, 2, 3 negatives right here. If you've got a negative cubed, you've got 3 negatives, and you've got this negative out here. There's 4 negatives. So once you combine that and multiply all that out, you've got 4 negatives, which makes a positive. This is y equals 2x cubed. That's not the same thing as what we started with, so I don't have y-axis symmetry. All right, so let's try origin. Origin. Flip both. Opposite y equals opposite 2 times opposite x cubed. So again, you've got 1, 2, 3, 4. You've got 4 negatives on the right side over there. So that's going to turn into a positive 2x cubed. But now we've got the negative y in the front. So you can isolate y by dividing by a negative. You're going to get y equals negative 2x cubed. That's the same thing as what we started with. So that tells me that there is origin symmetry. But this probably would have been easier if you just graphed it, okay? This graph looks like this. It's an x cubed, so it's a disco function. So the function looks like this, all right? If you took some point on that graph, so let's go this point right here. If you try the x-axis, it doesn't work. If you try the y-axis, it doesn't work. So there's no x-axis symmetry and there's no y-axis symmetry. But if you flip both, you're going here, then here, that one works. There is origin symmetry, all right? No x, no y, yes to origin. Next one, we can see this is a parabola shape, but the negative in the front flips it, and the 2 stretches it. That's a parabola with a flip and a stretch. I see my transformations. So instead of a 1-3-5 pattern, you may know a 1-3-5. It's actually going to be a 2-6-10 pattern because of that 2 stretches the thing. It's just going to be negative. So again, not real important to know that. But if you graphed that, you should be able to see the symmetry. Okay, if I took this point and flipped it over the x, is there x-axis symmetry? No. Okay, oh, I should have written origin over here. There's no x-axis symmetry. If I take this point and flip it over the y, is there y-axis symmetry? Yes. Okay, so there is y. If I do both, I'm here. So there's no origin. There's just y-axis symmetry. Even in odd functions. This is something that students kind of struggle with. It looks a lot harder than it is. I really want you to think hard about this. Even functions have this property. And it's kind of the same thing as what we were talking about before. Basically what that says is if you plug in negative x, you're going to get the same thing as what you would get if you plugged in x. F of negative x equals f of x, all right? Odd functions, if you plug in a negative or opposite of x, you get the opposite of the function. It's really hard to wrap your mind around those concepts without seeing specific examples, but that's a starting point. Most people are pretty good with this though. Even functions, if we're looking at a polynomial, all of the powers are even. Odd functions, all the powers are odd. Okay, all of the exponents are odd. Even functions have symmetry with respect to the y-axis. Odd functions have symmetry with respect to the x-axis. Now, end behavior is maybe what you're more familiar with. Okay, end behavior on an even function looks like up and up. Picture a parabola. Okay, if you make a parabola with your arms, both of your arms go up. Okay, if both of them go up or both of them go down, that's even. Even, same. Okay. For an odd function, one of them is down and one of them is up. And so I don't know which one's which, which one's first and which one's second, but that's kind of what happens. So the way that I think about this, that I think is useful, is if you imagine like a coordinate plane, okay, and I'll do this with my body sometimes, but like, let's say you've got an odd function. Okay, this is an odd function. All right, so this is my head, and the odd function is my arms. So let's just say, here I am. Okay, odd function is my arms. If you plug in some number, let's say we plug in 3, and we get some y value. Let's say we get, I don't know, 4. Okay. Then if we plug in -3, we should get what? -4. Okay, that's what an odd function does. Okay, that's what an odd function. If I plug in some number and get this positive value, if I plug in the negative version of that number, I'm going to get the opposite value right there. Okay, now change it to if my arms are now an even function. Okay, so now I'm an even function. If I plug in that same number 3 and get 4, when I plug in -3, what am I going to get? Also 4. Okay, so an odd function, you're going to get the opposite result, but an even function, you're going to get the same result. And I think looking at it like this man right here is probably the easiest way to understand it. So you'll see me doing that with my arms sometimes. Now this question is way easier than it should be probably. I don't need any of this stuff other than all powers are even or all powers are odd. It says determine whether the function is even, odd, or neither. So see how this is x to the 5th, x to the 3rd, and x to the 1st. That's an odd function. Okay, that's an odd function. And you see how this is x to the 2nd and x to the 0 power? That's even. And then this one, x to the 2nd, x to the 1st, x to the 0. See how they're not all even or they're not all odd? There's some, some are even, some are odd, so that's neither. Okay, so hang on. Don't leave yet. Okay. Part A is an odd function, and so odd functions have this property right here. Okay. And so what we do is we look at what happens if we plug in opposite x. And so if you took that function, and replaced x with opposite x, okay? If we took x and replaced it with opposite x, there are 1, 2, 3, 4, 5 negatives. So that's negative x to the 5th. There are 1, 2, 3 negatives. So that's going to be a negative 2x to the 3rd. There are 1, 2 negatives there. So that's going to be a plus 3x. Okay. Do we have the same thing as what we started with? We don't. We have exactly the opposite. Every single one of those terms is the opposite sign, right? I went from positive x to the fifth to negative. I went from positive 2 to negative. I went from negative 3 to positive. Everything's the opposite. And so f of negative x is equal to the opposite of our original function. That just means it's odd. Okay? Now, obviously, it was easier just to look at the odd numbers, but I'm trying to show you the definition. So look at part B. When we had this function, forget about the x0. If you took every x and replaced it with opposite x, that's what your function looks like. Okay? So I've got 1, 2 negatives once I square that. And that 2 negatives is going to make a positive. That's 2x squared. And then I've got that minus 3. You see how that's exactly the same as what we started with? That's the same. And so f of negative x is equal to the exact same function that we started with. That's what this says right here. That's what this says. That's an even function. Okay, but again, I know that's difficult to understand, and so I like to visualize this guy standing here. Okay, if you plug in an x number or a negative x number and you get the exact same value, that's even. Okay, but if you get that opposite value, odd. Okay, we'll do more of that later. Last thing, I believe, use the parent and transformations to draw a quick sketch of the graph. I believe you've done this before in algebra class, but what you would want to do for part A is you would want to notice, see how this is going to have an x squared in it? That's an x squared, so we know that's a parabola shape. That's the parent function. X squared is the parent. It's going to look like a parabola, but then this plus 4, do you remember what that does? Is it right? Is it left? That one's left. So we're going to take a parabola and shift it left 4. 1, 2, 3, 4. There's the vertex. Remember my 1, 3, 5 pattern. Okay. Transformations are pretty powerful when it comes to graphing because we can do this quick. All right. So we look at part B. And part B is also going to have an x squared in it. That's your parent function. So we know that's going to be a parabola shape. But we've also got some transformations. We've got right 1. And what's this plus 4 do? Up 4. And what's this negative in the front do? The negative is a vertical flip. So my parabola shape is actually going to be upside down now. So I go right 1, up 4, vertical flip. Right 1 and up 4. Vertical flip just means my 1, 3, 5 pattern is now going down. Down 1, 1, 2, 3, down 3, 1, 2, 3, 4, 5. That's my parabola shape. What's the basic shape of part C? It's a V shape, right? Absolute value, that's going to be a V shape. We know that's a V shape, but that means it goes left 3, and this means it's a flip, and this means it's a vertical stretch by 2. Okay. So a parabola has that 1, 3, 5 shape. A V shape actually just has a 1, 1, 1 shape. Okay. A 1, 1, 1 shape. Its slope is up 1 over 1, up 1 over 1, up 1 over 1. But when we vertical stretch it by 2, now it's going to be up 2 over 1, up 2 over 1. So what I mean is it essentially changes its slope. Instead of a slope of 1, it's now a slope of 2. Okay? So we're gonna go left 3, and that's where the vertex will be. but it's a flip. It's a flipped upside down V shape, but it's got a vertical stretch by 2. So instead of going up 1, we go 2. Oops, not there. Okay, last one. We've got a square root. Square root function. I think the square root almost mimics the shape of the function. I call it an eyebrow shape. But we're definitely going to take that eyebrow shape and go left 2, down 3. Left 2, down 3. Left 2, down 3. It's right there. And then your eyebrow also has a 1, 3, 5 pattern. It's just going sideways instead of up and down. So I can go over 1 and over 3 and over 5 would be like this. It's kind of the same shape as a parabola. It's just on its side. Now, don't forget about domain and range. We still should be able to find domain and range. So I'm not going to do it on all of them. But on this one, the domain would be from -2 to infinity. And the range, look at the y, would be from -3 to infinity. That's domain. That's range. Don't forget about that because we could do that pretty much on every single problem.